Welcome to my presentation. My name is Santiago Turriaga and I will be presenting high-performance computing simulation of granular media in silos. The index of the presentation will be as usual. First, a brief introduction to the problem and the proposed the motivation and the proposed solution. After that, I will be presenting the dynamic domain decomposition strategy we implemented, and next some results of our experimental evaluation, and finally some conclusions and future work. So, what is granular media? Granular media are conglomerates of discrete, solid macroscopic particles that conforms bodies of different shapes, dimensions, and composition, just like in the picture. They have broad application in the industry. Actually, they are the second most used type of material in industrial processes after water. For simulating this kind of material, the discrete element methods DEAM is a well-known method for simulating this type of materials that simulates the behavior of each one of the particles over time. This fact that simulates each one of the particles over time impacts in that when simulating large number of particles, the simulation usually requires a significant execution time, and so the DEAM these DEAM softwares include support for parallel and distributed computing in order to improve the computation of these simulations. In our work, we address the LIGHT's public DEAM software simulation, that it is a well-known open source software simulation software, that in fact supports parallel and distributed computing. However, it does not support dynamic workload distribution. So when performing large simulations, usually the workload becomes unbalanced, and this harms the overall performance of the simulation. In our work, we actually studied the case scenario of simulating the charge and discharge flows of granular media in silos using the LIGHT's public. This is a very relevant problem because usually the pressures exerted on these silos by the granular media becomes too high, and the silos ends up collapsing. And this has happened here in Uruguay, and people had died. So this kind of studies are quite relevant. Furthermore, in order to improve the performance of our simulation, we implemented a well-known domain decomposition algorithm for providing LIGHT's this feature of dynamic workload distribution. We implemented the mobile plane strategy proposed by Markauskas, so it's a well-known strategy, and we'll show that in the evaluation results that results were quite positive. So the dynamic domain decomposition strategy groups processes using a 1D decomposition strategy. That is, a group of processes shares the coordinates of a given axis, and the boundaries of the subdomains are defined by this axis. We had to, in order to implement our strategy, we had to define how a metric for determining the workload, that is the load of each process, and so we simply defined it as the proportion of particles contained in the subdomain where the process is assigned. To maintain this information, we had to modify the data structures in Lights Public to store and compute this load of each process. The workload reorganization and rebalanced during the simulation is not applied on every iteration because it will be too heavy for the simulation. So it's applied only when a certain threshold is met. We empirically defined this threshold as when a given process has at least 20% more load than any other process in the simulation. When this happens, we execute the mobile plane strategy and compute new boundaries for the subdomains. In order to improve this computation, each process computes its own load, and an MPI reduce operation is used to consolidate all the results. Once the results are consolidated and the reduction phase ends, a master process is given the task to centrally define the new boundaries for the next iteration of the simulation. Okay, so now that we have our dynamic decomposition strategy, we evaluated our implementation using the bin flow problem that simulates the loading and unloading of a silo. The simulation starts with loading, where the particles are inserted at the top of the silo and moved towards the bottom of the silo in freefall motion. And once the loading completes, the particles leave the silo through a hole in the bottom of the structure. Using this scenario, we generated different instances. We defined two configurations using 150,000 particles and another one larger with 450,000 particles. Two types of scenario for each configuration, that is the static scenarios, the default behavior of the Lights Public software, and the dynamic scenarios where our dynamic decomposition strategy is applied, and 4 instances of the problem for each scenario. 3 for the smaller scenario with 150,000 particles using 8, 16 and 24 processes, and only 1 for the larger scenario with 450 particles. Furthermore, we defined an instance with 150,000 particles, which was solved sequentially we use these results as a baseline for comparison. Okay, so the main results are presented in this table. We can see the standard deviation of the execution is quite low, so our confidence is high. Results show that improvement is reported over the same configuration instance using the static and dynamic domain decomposition strategy. So for example, the table shows that using 8 processes and the dynamic decomposition strategy, execution time improves by 34% when compared to the static decomposition strategy using also 8 processes. So improvement in execution time ranges between 24% and up to 42%. That is a significant improvement. And speed up, which is reported over the sequential execution, ranges between 6 over 6 and up to over 11. So speed up is also quite good. When comparing the speed up, the scalability of our implementation, we see that most gains are obtained when used 8 processes, and speed up continues to improve up to 24 processes, but deviates from the ideal speed up by quite a large margin. So gains are lower with when increasing the number of processes. This is a usual behavior in many algorithms using distributed environments, so it's not surprising. Well, now finally some conclusions on future work. In our work, we studied the charging and discharging process of granular media stored in silos. We implemented and evaluated a well-known dynamic decomposition method based on the mobile planes strategy. Our experimental methodology evaluated the efficiency of our implementation on different scenarios, and the main results indicate that the implemented method is able to improve execution time by improving workload balancing up to 42% in reduction in execution time. So we are happy with our results, and for our main lines of future work, we aim to extend the performance evaluation of our proposed implemented method by including larger scenarios, and we would like to study other granular media applications on science, such as astronomical bodies or other industrial processes, also using the LIGHTS public simulation software.